Hello, this is Games Without Dice or Cards, Combinatorial Game Theory. I'm Tom Morley. So let's start by jumping into the water head first, and let's play a game. Let me first introduce you to our two players. Our two players are called left and right. These two players alternate. One goes, the other one makes a move, then the first one makes a move, then the other one makes a move. Typically, left is associated with the color blue, and you can remember that because there's an L in blue. And right is associated with red, and you can remember that because there's an R in red. Now, these players are going to alternate playing, and the first one that can't move loses. So there's no ties at each stage in the game. There'll be various moves available to one player or the other player, or perhaps both, and whoever runs out of moves loses. So let's take a look at something like this. And let's start with a little horsey. Okay. So this is a game called Hackenbush. Well, it's a particular position in the game called Hackenbush, and you can start in various ways. But we start with this little horsey. The two players, red and blue, left and right, take turns, and what they do is cut one of their edges of their own color. So if blue starts, he could cut this edge, and that edge is no longer there. Now, these edges have helium in them, so and they're attached to the ground here, which is green. So if something gets disconnected from the ground, it floats off and is not available to either player. So, for instance, maybe right goes here. Maybe left goes here. Now, at this point, this whole piece here is still connected to the ground, but once right moves, it all floats up, and now left moves, and there's no moves left for left. Okay? So whenever the two players alternate, left cuts blue edges, right cuts red edges. Any edge that's either cut or no longer connected to the ground, to where the nutrients are, the nitrogen and the water and whatever, any edge that's no longer connected to the ground floats off and is not available to either player. When a player has no edges to cut, the game ends, that player loses. Okay? We'll see a lot of examples in terms of Hackenbush as the game goes on. Let's take a look at some very simple positions in Hackenbush. Here's the ground. It's green. And now we go, I don't know, blue and maybe a red in between. And maybe a red and then say a blue on top. Now, it's okay that these aren't connected, but they're connected to the ground, so that's okay. So they're there. Maybe red goes first, and red says, aha, I'm going to cut this, and now these float off, and that top blue edge is no longer available for blue. Blue say, what's the best move for blue? I don't know offhand, but blue might cut this, and then red cuts this, and then blue cuts this, and now red loses. So that's how that works. And we'll look at various variations of this where we start with more complicated pictures and try to analyze in terms of who wins. If left goes first, who wins if right goes first. Okay, let's take a look at another class of games. And This is a class of games all played with coins. In this case, the coins are pennies and dimes, but and maybe right is pennies because the copper in pennies, although there's very little copper actually in pennies, looks kind of red. And then the dimes, say, are left. Now, both players push coins to the left in the direction of that. And the three games, push, shove, and run over, have slightly different rules. Now, you can push a coin off the edge, off the end, and if it's off the end, it's no longer in play. So the two players alternate, pushing one coin to the left, one space. And let's look at say this position here. In push, that's the first game. If left pushes this coin over this coin over one, then that pushes also the coin next to it over. So that's called push. In shove, when you push a coin over, everything to the left moves over one space also. So in shove, this coin over here gets thrown off the cliff here. In run over, what happens is when you push, say, this coin over here, one to the left, you run over that person, and that coin disappears from play. So you can look at longer positions to start with, different relations of coins on the thing. I think it's not too hard to show. Whoever has the rightmost coin will win the game. But if we have several of these going at once, then things get a little bit more complicated. And still, what we want to do, even if we know who wins the game, what's the best play, maybe to delay going off the cliff as long as possible. So here's 4 games to play with, and I urge you to start with pictures like this. Find someone to play. Figure out whether you want to be left or right. Doesn't matter. Draw a picture like this and go play some games. Get some coins out. Draw pictures like this. Play several of these at once, and we'll explain as the course goes by how to do that more carefully, and see what looks like good moves and see what looks like bad moves. So there are some games to start with, and let's continue next time. Well, good morning or afternoon or evening, as the case may be again. What we want to do today is just say a little bit about what is and is not a combinatorial game. All right. No dice. No dice. No cards. No randomization at all. So Monopoly has dice. It has you pick cards from the 2 piles. Monopoly isn't a combinatorial game. All right. There's 2 players. At least for what we're doing. The 2 players, we call it left and right, call it A and B. Bob and Susie, whatever you want, there's just 2 of them. They're different. Solitaire is not a combinatorial game because there's just 1 player. So combinatorial games, there are 2 players, no random moves. No ties. Ooh, that looks like 1 word. No ties. All right. So chess can actually have a draw. That's when neither black wins nor white wins, but they tie. And so according to this, chess is not a combinatorial game. There's no dice in chess. There's no cards in chess. there are two players, but there is a tie. Now, eventually, we'll weaken that assumption and allow for combinatorial games with ties. But for the time being, let's only look at moves and games that are that have no ties. So either blue wins or red wins, but not both and not neither. Also, it's finite. The game ends in a finite number of moves. We might not be able to say ahead of time how many that is, but we know that's finite. It doesn't go on forever. Note that this is different than saying that there's only a finite number of options available to each player. You can have games where there's infinite number of things the players can do, but it still has to end in a finite amount of time. And so we think of this in the following way. The two players alternate playing the game, and when the first player that it's his or her turn, and there's no moves that that player can make, then that player loses. So in terms of chess, once you're in checkmate, there's no move that you can make, and therefore you lose. Two other things that are close to combinatorial games, but not quite, which we'll look at are Go. And you can look up the details of Go. Go is an interesting game. And also, you may have played this game in grade school. And it's called, or maybe high school or college, you never know. It's called Dots&boxes. So players alternate drawing lines, and when a player completes a box, you put your initials in the middle, and you have to move again. The score then is the total number of boxes. And if you work out, if the number of boxes is odd, then one player or another must win. So in that case, it's a score, but we can think of it in terms of the score determining who wins. But again, there's no ties. Each box is either red or blue, and if there's an odd number of boxes, then one player or the other must have more boxes at the end. This is actually a fairly complicated game in terms of its analysis. We hope to say a little bit about it towards the end of the course. Okay, so these are kind of what is and isn't a combinatorial game. There are actually many things that are very close to combinatorial games in terms of ties and whatever. These we'll eventually look at, but for the time being, we want to keep things fairly simple. Two players, no random moves, finite, no ties. And that's where we're headed. Okay, here's the problem for you all to think about. This may be easy, it may be hard, but here's a Hackenbush position. The two players are left, who is blue, and right, who is red. And the problem is, if left goes first, who wins? And if right goes first, who wins? Remember that the players alternate. Left alternates and cuts down blue edges. Rights can only cut down red edges. And for instance, if blue cuts down this edge down at the bottom, then this red edge here floats off. It's full of helium, floats off, and is no longer available to right. So work on this problem. Don't look at the answer immediately. Go and sit down with a piece of pencil, paper, pen, or whatever, and see if you can figure out who wins in best play if left goes first, who wins in best play if right goes first. All right, so you want to look at the solution of this. So let's try to solve it. This is not the only possible argument, but let's try to see what's going on. So if blue goes first, that's left, then there are only two edges available for blue, and they're more or less the same. So blue will cut this. Now, if you think about it, and that therefore this right edge, this red edge up here floats off. Right can either do this or this, but right's best move is to move here, because if right doesn't cut this now, then blue will cut down the blue below it next time, and then right will be without a move. So right, that's the best move for right after blue does this. So let's label these 1, 2. Then blue left only has one move left, so that's got to be this one, 3. And then right only has one move left, so that gets cut. That's 4. And now it's blue's turn. It's left's turn. No moves available, so left loses. So if left goes first, then left loses. All right, let's take a look and try to see what happens if right moves first. Right moves first. Again, you can either look at all possible cases, or you can look at it and try to figure out what the best opening move for right is. And the best opening move for right is either this one or this one. Because of this threat from left to chop down below and get rid of that right move, right may as well take this move while he or she can. Now, left, at this point, might as well chop down a right, and so that happens. And now this right is unavailable. This all floats up off the page. Let's see. It's now right's turn. So this was 1, 2. Right's turn is 3. Right cuts that. And now left cuts this. And now it's right's turn. And there's no moves. So right loses. Going back to the original picture, this says that if right goes first, right loses. Okay, so if you got this, great. Make up other things and try them out for yourself. If you had some difficulty with that, let us know what the problems were. Go through the solution carefully and see if you can't puzzle it out. And we'll see you on next time with week 2. Take care. Welcome to week 2. Games without, oops. What do we got here? Dice. No dice. Cards. No cards. No cards. No cards. No dice. No random moves at all. Games without dice or cards. Combinatorial game theory. I'm Tom Morley again. Welcome. So, in the study of these simple games, what we need in order to look at examples by hand is a whole bunch of games. We have a couple that we've looked at already, and we'll look at again this week. But I want to introduce you to a new game. A new game is called Cupcake. Okay, in this game, like all the other games that we've looked at, the players are left and right. They move alternately. Left moves, then right moves, then left moves, then right moves. And the first player who has no move at all loses. So Cupcake is played on squares like this. That's 2 by 2. You could start off with a 3 by 3, a 10 by 10, a 6 by 4, whatever you like. And let me show you the various moves that are possible just in this example on a 2 by 2. Left always cuts up and down. Right always cuts left to right. Okay. We'll actually look at a couple of other cut games before we finish the course, and we'll always use this convention. Left cuts up and down. Right cuts left to right. Okay. So if left goes first here, left is the only possible move is left to cut the center seam here. Oops, left cuts up and down. Got that backwards. Okay, so left goes up and down like this. That leaves two pieces like this. Now, what is right's move in here? Right doesn't get to cut in both of them. Right has to pick one or the other and cut in it. We see they're approximately the same no matter which piece right picks. If right picks, say, the first one, right cuts across like that. That's the way right cuts. That leaves two pieces here. In both of these pieces, no cuts left are possible. They've been cut into small squares. There's this piece left here, which right has a cut in. But remember, it's left's turn next, and left has no move. Left loses. So in this cut cake that's 2 by 2, if left goes first, left loses. You might want to look and see what happens if right goes first. Try it out. Try it out for yourself. Let's remember a little bit about Hackenbush, and let me actually extend the game slightly. Hackenbush is played on, we have this ground here, which is green, the green grass on the ground, and growing out of the ground is a red, blue, green plant of some sort, okay? The edges are red, and right can cut the red edges, and the edges are, some edges are blue, and blue edges can be cut by left, so right for red, right has an R in it. Blue for left, blue has an L in it. And the green edges can be cut by both players. Now, these green edges are new from last time. And I'll try to point this out. On some monitors, this looks very similar. The blue and the green look very similar. I'll try to point out when there's some confusion. Okay, let's look at this example down here. We have this whole plant here. Suppose it's right's move, and right cuts by the pencil mark this right edge. This right edge then disappears, and then everything that's not hooked up to ground also disappears. So once this red edge here is disconnected, this whole piece of the plant here will die because it's not connected to the ground, so we erase all of that. So players alternate. Right cuts right edges or green edges. Left cuts blue edges or green edges. Each time you cut an edge, that edge disappears together with everything above it. And the first player who can't move loses. All right. Now, it's fun to play one game at a time, but it's even more fun to play 5 or 6 games all at once. So, I don't know. Let's play over here. Let's play a game of chess. Over here, let's play a game of Go. Over here, let's play, I don't know, a cut cake of some sort. Let's play a Hackenbush. Suppose some of these edges are green and some are red. I'm not going to draw it. I just mean this to be schematic. Over here we have a nim heap of some size. And let's play all of these at once. Now, what do I mean by playing all of these at once? Well, the players now alternate. But instead of playing one game or the other, you pick one game out of the 5 and make a move in that game, and that's your turn. The other player If you're left, say you do that first. The other player, say right, picks one game out of the 5, makes a move in that. Okay. We note the following. Even though the players go left, right, left, right, left, right, left, right, in each of the individual games, the players need not, the plays in that inside that individual game need not be left, right, left, right. Because left might make a move in here, and then right moves over here, and then left moves again over here. So in the individual games, we need not have left, right, left, right, left, right alternation. But in this combination game of playing these games all at once, we do have left, right alternation. Now, if these individual games are called G, H, K, L, and M, then playing these games at once, simultaneously, like we just went through, is called the sum of the games, and is written just like ordinary sums. So G plus H plus K plus L plus M represents the game. We have these 5 games, I guess. Let's see, 1, 2, 3, 4, 5. I'm not very good at numbers, but I think there's 5 games there. We have these 5 games, and then each player, left and right, in alternation, picks one of these games and makes a move in that one game. Now, the first player who can't move at all loses, just like we have in all our other games. So you can't move after you're checkmated. Go, you can't move after you lose. Cut cake, we know the rules for cut cake. Hackenbush, we know the rules for Hackenbush. We have a pile of 4 coins here. So whoever once the coins are gone, then there's no moves there. So once there's no moves left in any of these games, then there's no moves left for that player, and that player loses. So let's maybe look at an example and try to play through part of the game. So here we have a cut cake and 2 Hackenbush games. And we've been looking at left first for a while, so let's do right first. So suppose right moves first by cutting this in 2. Therefore, what's left there on the table is one of these and another one of these. And now, it's in some sense, this is now 4 games. This game, this game, this game, and this game. Now it's left's move. Left, I don't know, what does left want to do? Left, say, cuts one of these off. And so this now becomes and now we have this game, this game, this game, this game, and this game. Right has a move. Right maybe cuts this off. That gets rid of the blue also. This all goes up in the air. There's no moves left in that game. Left's move again. I don't know. Left might cut off another square down here. And we can continue on left, right, left, right, left, right. And I think in a move or two, you'll see that left can win this game. So try that out for yourself. All right, welcome back. None of this, none of these. No dice, no cards, games without random moves. Now that we know from last time how to add things up, add up games, and we play them simultaneously in the ways we described last time. We want to talk about what it means for 2 games to be equal, which is going to mean something like whenever we play these games together with some other game, the same thing happens. Now, I want to be much more precise about that in a minute, but that's essentially what's going on. And so to start this, I want to start with a simple, very simple case, and our definition of when a game is 0. This is a definition. In mathematics, definitions are prescriptive. That means they're what is the case. Okay. So what does it mean for a game to be 0? And this means in best play, the first player to move loses. So just like the 0 game, whoever moves first in the 0 game loses because there's no moves. Let me show you. The 0 game in Hackenbush is this. Nothing to cut. The 0 game in a nim heap is a heap of 0 coins, which you can see over here to your left. And so that's the 0 game. And then we'll say that the game is equal to 0 if in best play the first player to move loses. Okay, let's look at an example. Nim heap of size 2 over here, nim heap of size 2 over here. It just matters that there's 2 dice over here, 2 dice over here. The numbers on the dice don't change anything. So if whatever left does over here, right does over here. Whatever left does over here, right does over here, and left loses. So if left goes first, left loses. Similarly, if right goes first, right loses. So this game, 2 nim heaps, a nim heap of size 2, which we notate this way, plus a nim heap of size 2 is first player lose, so it's equal to 0. Okay? So we know what a game is equal to 0. So now let's try to see what a negative of a game is. If we have a game G, we can have an associated game called minus G. Now let me show you this for Hackenbush. Say this Hackenbush game is G. Then minus G is the same thing with left and right interchanged. Okay. Now let's look at other possibilities. In Cupcake, remembering that right cuts left to right, and left cuts up and down, then if that's a game of Cupcake, if we simply interchange rows and columns, then whatever became a possibility for left is now a possibility for right, and whatever became a possibility for right is now a possibility for left. Okay, so the negative of this Cupcake game is this game. The negative of say, nim heap of size 3 is now interchanged versions of left and right. But since left and right have the same moves in them, the negative of this is the same as that. So the negative, let's do it, of a nim heap of size 2 is a nim heap of size 2. Interchanging left and right in nim doesn't do anything. What is it in chess? Well, the negative of the negative chess game is a chess game where black goes first, I guess. Or maybe it's the negative of a chess game is where you, instead of you having white, you have black. So it's the interchange of the two sides. Left becomes right, right becomes left, black becomes white, white becomes black, whatever the moves in the game are. In Go, the negative of game would just correspond to a different player going first. So instead of white stones, you have black stones, et cetera, et cetera. So that's how a negative of game is. And now we're ready to define G equals H means G minus H is 0. Well, G minus H is just an abbreviation for this. Okay. We'll look at some examples for next time. This is the short one. Let's just take a look at, give you an example to work on yourself. Let's look at a cut cake. And a Hackenbush, and my claim is, are these equal? Try it out and we'll see next time. Take care. Welcome back. None of these, none of these. You know the rules by now. No random moves. I'm Tom Morley. Last time we were looking at these two games. The left is a cut cake, and I always have to remind myself, right cuts this way, left cuts up and down. And the right game is a Hackenbush. It's a very simple game. Left has one move. Left can cut this left branch. Right has no moves. Left goes first, left wins. Right goes first, left wins. Left always wins in this game here. These are two games, G and H. We want to know, is G equal to H? And to do so, we have to look at G minus H and see who wins. If this is 0, then the games are equal. To say that this is 0 means that, and minus H is, of course, an abbreviation for G plus the negative of H. We'll go ahead and just write it that way. And say this is equal to 0 just means that whoever moves first in this game loses. So we have to analyze the strategies in best play in G minus H. So let's look at G minus H. G minus H is cut cake over here. And the Hackenbush over here. But the negative of the Hackenbush is this. Now, let's look at right. What happens when right goes first? Okay, so let's look at right going first in this game. The best move for right is to chop down the cherry tree in honor of President's Day, which is coming up, except by the time you see this, it's already passed. Left's best move at this point is to chop this in half. Right then has to take one of these 2x2s, it doesn't matter which one, and chop it in half. And now look and see what's going on. Left has 1, 2, 3 moves, and right doesn't have much. So actually, there's a little bit more work to be done here, but left has lots more moves here than right ultimately does have. And so it turns out that in fact right loses. And there's a bit more in the whole process, but you can puzzle that out and try it yourself. You also might want to try if left goes first. Left goes first. The easiest move for the best move for left going first is to chop up and down in the middle, but still left loses. So in this combination game of this cut cake and this Hackenbush, the sum is first player lose. The sum is 0, and therefore this game here happens. Okay, so we've done a couple of simple examples. One thing that we haven't done, which you might think about, is show that any game is equal to itself. That is to say, any game minus its negative equals 0. And the basic idea of showing this is what Conway and friends called Tweedledum, Tweedledee principle. If you have a complicated game over here, and it's negative over here, then whatever one player does over here, the other player will do the opposite over here. Whatever one player does over here, the other player will do the opposite over here. So what that says, the second player to move always has an advantage because there's always will be a counter. Whatever you do in one of these, the other player does the opposite in the other one. The branches over here that are right branches over here are left branches. The branches over here that are left branches are over here right branches. So if left moves over here, then right moves over here, for instance. In general, this says any game is equal to itself, and not a terribly surprising thing, but that's how we'll end the first week. And we'll come back, check out some problems for you to work on in the homework/quiz. It'll let you know how you're doing in the course, and we'll go over them afterwards. So take care. So over here I have 1, 2, 3, 4, 5, 6 games. A Hackenbush, 1 green edge, 3 blue edges. A Nim heap of size 3. Cut cake, remembering right cuts left to right, left cuts up and down. Another Hackenbush, left cuts blue edges, right cuts red edges. Another Hackenbush, and another Hackenbush. This one is, in some sense, not very interesting all by itself because right just cuts the edge if right goes first. If left goes first, left has no moves. So they'll go back and look at the various games. Hackenbush, 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 cut cake, and Nim heap of size 3. Here I'm using dice because I didn't bring any quarters with me this morning. So in all of these games, what I want to look is left going first. Who wins? Who wins A plus B, the sum of these two games? Who wins C plus F? C plus F. E plus F, who wins this game? And D plus E plus F, who wins that game? This is the quiz for the first time in week 2, so this will take a while. And we'll see you all next time. Take care. Welcome to week 3, Games Without Dice or Cards, Combinatorial Game Theory. I'm Tom Morley. Today we want to talk about ordering games. And these are our definitions. Games are like numbers, sort of, or at least sometimes. And numbers you can order. 1 is less than 2 is less than 3. 2 is equal to 2. Minus 1 is less than 6. Here's what this means for games. To say a game is negative means that right always wins, going first or going second. To say a game is 0 means the first player loses, whoever moves first loses, and the second player wins all the time. To say a game is positive means left wins always, going first or going second. And here's a new one for you that doesn't come up in numbers. A game is fuzzy with 0. That's how that's pronounced. If fuzzy, F-U-Z-Z-Y. It's fuzzy with 0 if the first player wins. So let's look at what these mean and how they're used. First of all, the way they're typically used is not comparing a game with 0, but comparing one game to another. So G is less than H. Actually, you just convert and subtract G from both sides, and this should be the same thing as saying that 0 is less than H minus G. That's what it is. The definition is mathematically. What it means in terms of gameplay is that H is better for left, even if it's part of a bigger game. And we'll have some examples as the week progresses. So H is better for left than G, even if they're both part of a much larger game. If you're playing 5 games at once and one of the pieces is G, replace it by H and the whole thing is better for left. Now you can also, of course, read this backwards. This says G is better for right than H is, because to say that something is less than something is the same thing as saying that is bigger than the first thing. The interesting case perhaps is equal to 0. G is equal to H, and this is our definition, means H minus G is 0. And what this turns out to mean is that G and H have the same outcome, the same player wins in best play, even if G and H are both part of some bigger game. So you have a Go game, and towards the end you have this little piece in the corner that's equal to G. Well, replace it by that little piece in one corner by H, and nothing has changed in terms of the outcome. Now, in real numbers, you can say not only that one number is less than another number, but you can also say 1 is less than or equal to 2, or 1 is less than or equal to 1. And so you can combine these inequalities, and for instance, in the following way. G is less than or equal to H means, just like it would for real numbers, G is less than H or G is equal to H. So let's see what this says. It says to say that G is less than H means that H is better for left than G is, and to say that G is equal to H means that they're the same for left and right. So you put these together, and less than or equal to means H is at least as good, perhaps not better, but at least as good for left as G. In other words, it's saying left wins H minus G going second. Okay, so that's a lot of stuff. Bunch of definitions here. If you forget the definitions, go back, look them over. They're all right at the beginning of this module, and we'll continue on in the next module with the definitions, with some examples. Welcome back. Still week 3. What we want to do is take a look at an example and see how we can use inequalities to analyze games, and how we can use inequalities to simplify games. The example I want to look at is this example here in Hackenbush. This is the game G. There's the ground here. The ground is green. A blue edge, a red edge, and a blue edge. This is Hackenbush, and if you go back to week 1, or at some point there should be a dictionary on the site with how various games work. Players alternate. Red can only be cut by right, blue can only be cut by left, and once an edge is cut, not only does that edge disappear, but any edge that's no longer connected to ground will also disappear. So if you look at the possible left moves, left can cut this blue edge on the top, in which case what is left is just blue, red, like this. Or blue can cut the edge down at the bottom, in which case what is left is just nothing. Now, what I want to do now is give you another way of writing out games. Another way of writing out games, and you'll see this on any of the references that we look at, is left curly bracket, and now list the possible left moves, and then a pipe in Unix, verticals up and down, and then list the right moves. So the possible left moves are chop off the bottom blue edge, and that's 0. This game is 0. Whoever moves first loses. Now the other possible opening move for blue is, or left, is to cut off the top here, and that leaves this. And a while back we called this game 1/2. And it turns out this game plus itself is equal to 1, so we might as well call this 1/2. Now, the possible right moves are to cut off the red edge there, in which case what's left is just one blue edge, and one blue edge is one move for left, and that's the game 1. We'll call that the game 1. So this game up here can be represented abstractly as the game where the left moves are to 0 or 1/2, and the right moves are to 1. Now, you can prove, or you can go through the details, or you probably would guess that 0 is less than 1/2. That's true. Just look at 1/2. To say 0 is less than the game means left wins the game 1/2, going first or second. And look at this game up here, 1/2, and we see that left always wins. Left going first cuts the blue edge. Right has no move, right loses. Right going first cuts the red edge, then blue cuts the then left cuts the blue edge, and again, left wins. So 0 is less than 1/2, which means that 1/2 is always better for left than 0 is. So what that says is there's no reason whatsoever that left would ever choose 0. 1/2 is always better, so this game is the same as this, and now we've simplified the game to an equivalent game with fewer possible moves. We've deleted the moves that are no good because of inequalities. Now, in terms of right moves, there's only one right move here. But if there were several right moves, we could delete all but the smallest, because right wants moves to be small and left wants moves to be big. Okay, so let me end with a problem, and this is for you to work on. Here's two games, G and H, and see if you can prove that G is less than or equal to H. If you remember right, that says that H minus G wins for left going second. So you can work that out. Okay. Here's an outline of the problem solution. So we were asked to show that G is less than or equal to H. That's the same thing as showing H minus G is greater than or equal to 0. There's H. Here's minus G. So all we have to do is left moving second wins in this game. Now, if right moves first, right's only move is to chop this. Now left has a move of chopping this. Now right has no move, left wins. Welcome back. There's still no chance. There's no chance the cards ended up like this, because that's a perfect faro from new deck order. Today we want to look at an example. Ski jumps with jumps and ski jumps without jumps. And we'll start with ski jumps with jumps and ski jumps without jumps. Now, let's first talk about without jumps. It's played on a board that looks something like this. We can have many more different rows. The rows can be different lengths. And in each row is a counter. The penny here represents left, and the dime here represents right. And you have whatever you want for the starting configuration. You can have, there's just one counter per row. You can have as many rows as you like. The rows can be as long as you like. Here's one instance. The penny that is left always moves right.
the dime that is right always moves left. And as usual, the first player that can't move loses. And so let's play the game with left going first. Left moves, then right moves, left moves, right moves, left moves, right moves, left moves, right moves, and left has nowhere to go. So left has no move, it's left move, so left loses. So when left starts, left loses. Let's look and see what happens when right starts. It's almost exactly the same, only upside down or something. So right, left, right, left, right, left, right, left. It's now right's turn. Right has no move. You have to stay inside the board. So right has no move. It's right's move, so right loses. So when left starts, left loses. When right starts, right loses. And that says first player loses, which is another way of saying that it's 0. First player loses. Now let's look at the possibility of jumps. The possibility of jumps makes it a much more interesting game, I think. With jumps, let's see what a jump is. When we have two counters like this, one directly above the other, of different, one's left and one's right. In our game, left will be above right, but depending on the initial configuration, right could be above left. If they're over like this, and it's left's move, left has two options. Left can continue on to the right, or left can jump over right and end up down here. So, for instance, when if the configuration is like this, and it's left's move, left can either move to the right, like this, or left can jump over right and end up down here. That's what a jump is. It's always optional. And so let's see what happens. Let's start off like here and look at right going first. Right goes first, left going first. Left goes first, right, left, right. It's now left's turn, left jumps. Right continues on to the left. It's left's turn, it's right's turn, it's left's turn. Now it's right's turn. Right has no move, and right loses. So when left goes first, right loses. As before, when right goes first, right loses. Right doesn't have any possible jumps here. So going second, left wins, and going first, left wins. That says the game is positive. So this initial configuration of ski jumps with jumps is always a left player win going first or second. So it changes with jumps. Now, so it's positive. It's bigger than 0. And so the question is, how much bigger than 0 is it? So let's compare this by trying to play the game G plus minus 1. So we play several games at once. We can either play in here or we can play in here. This is a Hackenbush with one red stalk, and so that's the same as minus 1. It gives a free move to right, and there's no moves in there for left. Let's look and see what happens. What happens here, the interesting case, and there's a couple of cases, you can work out several of these yourself. So when left goes first, now it's right's turn. Right can cut the stalk, and now it's left's turn, and left has nowhere to go, so left loses. So when left goes first, left loses. When right goes first, left also loses. And so, and you have to check that. It's a small game, so you can check that. So what we have is that G minus 1, right always wins, first or second. Best play. Let's see what that says. If g minus 1 is less than 0, then just add 1 to both sides and you have g is less than 1. We already know that g was bigger than 0, so g is somewhere in between 0 and 1. The question is where? And the answer is we'll see in a little bit. Okay, there we have it. And stay tuned for the next little piece. Thank you.
Games without dice or cards, combinatorial game theory. I'm Tom Morley, and glad you're back. We've been doing a lot with games, and some of these games were numbers, and they behaved like 1, or they behaved like -1 or 0, or 1/2 in one case. Not all games are numbers. Some games are much weirder than numbers. So let's take a look at this simple game. It's Hackenbush, where you have one green edge. Remember, the green edge, green edge can be cut by either left or right. And this game has a name. It's called Star. Okay, now let's see who wins Star. If left goes first, left cuts and right has no move. If right move goes first, right cuts and left has no move. So whoever goes first wins. That says Star is fuzzy with 0. There aren't any numbers that are fuzzy with 0. And to make matters worse, Star plus Star is 0. Let's check it out. Here's Star, here's Star. If left goes first, he cuts that, right cuts that, and that left has no move. So whoever goes first in Star plus Star loses, and so Star plus Star is 0. So that's not a number. Numbers can't behave that way. Here's another example, and it goes back to illustrating our new way of writing out games. This is a game called Up, and it's written this way. And it's the game, the left option, left can move to 0, and that's the only possible move. And right can move to Star, and that's the only possible move for right. So let's look at Up and see who wins Up. Okay, so let's see who wins Up. Up is 0 Star. If left goes first, left moves to this 0. 0 has no moves for anyone, so left wins because right has no moves. If right goes first, right's only move is to Star, which is this, which is the same thing as 0, 0. There we go, yes. So right then moves to Star, and here's Star, and left moves to 0, and now right again has no moves. So left going first, left wins. Right going first, left wins. So that says that Up is bigger than 0. But Up is not a number, and here's why. What I want to do is show that, in fact, Up is less than 1 over 2 to the n, for any n. Now, 1 over 2 to the n is a Hackenbush position where you have one blue edge and then a whole bunch of red edges on top. And to show that Up is less than 1 over 2 to the n is the same thing as showing that 2 to the n minus Up is greater or equal to 0, which is to say that left wins this game, going first or second. So here's 1 over 2 to the n. Here's minus Up. Reverse the moves for left and right, and reverse all the moves for left and right in the options. And so all we have to do is show that left wins going first or second. So let's look. So you try this. And we'll be back with the solution in a little while. So here's an outline of how to show that 1 over 2 to the n minus up is positive. Let's just look at the left going first move. If left moves first, I'd claim that the best move for left is to play to this star. What's left is then 1 over 2 to the n plus star. Now it's right's turn. What can right do? Right can move from star to 0. Remember that the only option in star is for left to move to 0 or for right to move to 0. In which case, what's left is 1 over 2 to the n. Left just chops the blue edge, and now there's nothing left, and so left wins. The other possibility is for right to cut off one of these red edges, and that just delays things. So right cuts off one of those edges. Left then moves from star to 0, and what's left is right cuts off another red edge, blue cuts off the blue edge, and now left wins. So that's the argument when left goes first. When left goes second, there's a little bit more stuff to do, but the argument is very similar. And again, if left goes second, left wins. Put this all together, and that says that 1 over 2 to the n minus star is positive, which says with what we did previously that up is bigger than 0 and less than 1 over 2 to the n for any n, and there's no number that does that. So up is not a number. Okay, that ends week 3. I'll post a little quiz, and I'll talk through it for the last part of week 3. Okay. So the quiz for week 3 is, I have a whole bunch of games. You have to decide in each game whether it's positive, negative, equal to 0, or fuzzy with 0. It can't be 2 of these. It has to be exactly 1 of these. The first game is the Hackenbush with 3 stems like this. The second one, Hackenbush with 1 green stem and 1 blue stem. Game number 3 is 2 copies of 1 green stem and 1 red stem. And number 4 is a little bit more abstract. Go back and look at the definitions of up and star and figure out whether up plus star is positive, negative, 0, or fuzzy with 0. Work this out, and we'll post the solutions by the time you see this. Take care. Okay, welcome to Games Without Chance. None of that. Okay, I'm Tom Morley, and let's see where we are. This week, we're doing the following. Some numbers are games, and that's where we are right now. Some numbers are games. Okay, so let's look at Hackenbush. This was a game we looked at from the beginning. Here's our ground. Here's a blue edge. Blue is left. Left can cut blue. Here's a red edge. Red edge is going to be cut by right. Now, this was a game that we looked at, and we computed a while back that 2 of these, copies of these, together with 1 red is 0. Whoever moves first in this game loses. If blue moves first, cutting blue edges 1 at a time, and alternates with right, who cuts red edges, then if left moves first, left loses. If right moves first, right loses. This is a 0 game. This is -1 here. So I might as well call this 1/2. 1/2 plus 1/2. -1 is 0. So this game here is a number. Now, suppose we have 2 of these. We have a blue, but 2 red on top. Now, there's no reason for right ever to cut the bottom red. So right might as well cut the top red. And it turns out that it's a four-letter acronym. It turns out that this behaves like 1/4. You take two of these, and they add up to -1/2. There's a half. -1/2 is reverse colors. Now, in general, we have the following games. So here's 0. There's 0. There's the 0 game right there. Okay, a picture of the 0 game. I should hang this up on my wall. There's the 0 game. Let's see. Here's so that's 0. This is 1. Here's 2. Run out of ground. Let's put some more ground over here. Here's 3. 1, 2, 3. We have the negatives of these. This, for instance, is -2. We have some fractions. Here's 1/2. I'm going to do a bunch of these. Wait. Here's a half. This is a quarter. This is an eighth. This is a 16th. And you can guess that when you have one blue and a bunch of red on top, you end up with a 1/2. Now, once you add these all up, so you can take any of these and add them up, what you can get by adding up these games is anything of the form p/2 to the n. P is any integer, n is any integer, and these are called the dyadic rationals. So all of the dyadic rationals turn out to be games. They all turn out to be expressible in terms of Hackenbush. So let's look at a problem. Y'all can try. What number is this? These two games. This is one game. This is the sum of two games. What number is this? Okay. Here's the solution. This is 1/4. This is 2, and 1/4 plus 2 is 2 1/4, also known as, what? Let's see, 2 is 8, 9/4. So either answer would be correct. And that's the end of Module 1. Games without chance. Oh, I did well this time. I just dealt that to myself, but that was a chance move. Actually, it wasn't. But this is Games Without Chance. I'm Tom Morley. Here we are this week. We're now in the module, Some Games Are Numbers. So let's go back and look at this alternative way we have of looking at games. Left options, right options. Okay. We can write down in terms of this notation the games that we looked at last time. 0 is no options for left, no options for right. 1 is 0 for left and none for right. 2 is 1 for left and none for right. And we can get some of the fractions this way. Okay, so here's the plan for this module. We want to look at games that are given in this form and try to figure out what numbers they are. Now, the reason why we want to figure out what number a game is because we know that positive numbers are positive. And in positive games, left wins. Negative numbers are negative. And in negative games, right wins. Zero games are zero. And in zero games, whoever moves next loses. So if once we know what number a game is, we know who wins. So this is partly to do with connecting up games and numbers, but also partly to do with figuring out who wins. And if we have a sum of games that are all numbers, all we've got to do is add them up. And numbers add up like numbers. 1 plus 1 is 2. You can prove that, I bet. Okay, so let's take a look. So we know that 0 is this, but we also know that there are other games that are equal to 0. A game is 0 if its first person lose. Okay. And any game that's 0 behaves like 0, like over here, even in a larger context. So let's look at the game -3, 1. My claim is that this is 0. Why? If left moves first, then left's only move is to -3. And now right wins because -3 is negative. If right moves first, right moves to 1. That's the only option for right. And 1 is positive, so left wins. So if left moves first, right wins. If right moves first, left wins. That's a first player lose, so this game is 0. And I think you can actually get a much more general result that if you have a negative number over here and a positive number over here, then any game like that has got to be 0. Let's take a look at another example. Let's look at, let's do 1, 4. My claim is that this is equal to 2. Now, what do I have to do? I have to show that 1, 4 minus 2 is 0. That is, whoever moves first in this game loses. If left moves first, left has, remember, -2 is nothing minus 1. That's -2. That's, and in -2, left has no moves. So in this game, left has no moves in -2, so if left goes first, left moves to 1 over here. What's left is -2, which is -1. So if left moves first, left moves to this 1. We still have this -2 over here. 1 minus 2 is -1, and right wins -1. If right moves first, there's 2 moves to consider. Right either moves to 4 minus 2, which is this 4 minus 2, or to 1, 4 minus 1. In either case, there's a little bit of work to do, but left wins. So there's a lot of games written this way that aren't the same, aren't the identical game to the Hackenbush games we looked at before, but nonetheless turn out to be numbers. And so here's one for you to try. And next time, we'll look at trying to figure out if it is a number, what number is it? So try this one, -4 minus 1. What number is this? The answer is that it's -2. It fits in the middle. And we'll see that's the key, one of the key steps. And so to actually prove this, you would have to show that minus 4, the game minus 4 minus 1 plus 2 is 0. That is, whoever moves first in this game loses. Okay. In 2, right has no move. So if right goes first, right has to move to this minus 1. We still have minus 1 plus 2, which is 1, which is positive, and so left wins. So there's half the argument, and the other is a little bit more complicated, but I think y'all can handle it. Games without chance. Okay, I just dealt myself a card hand by chance, and look what I got. You believe that? Okay, but no chance moves. This is the module, simplicity. It's all about simplicity. Okay, let's look. What do I mean by simplicity? Remember last time we looked at things like, well, let's do minus 3, 1. Now, it turns out that this is some number. And the number has to be between 1 and minus 3. Whenever you have a game like this that's a number, all the options over here are less than, strictly less than, all the options over here. It turns out that unless that happens, it's not a number. There are lots of games that aren't numbers. But if it is a number, it has to be somewhere in between. But you see, we have lots of choices here. You know, minus 2 is in between. Minus 1.12345 is in between. All kinds of numbers are in between. And if you actually believe in real numbers, which some people do, I happen to believe in real numbers sometimes, there are infinitely many numbers in between. And so we have to decide which one. And the answer is the simplest one. Simplest one. So this is some number. It's got to be, if this is some number, it's got to be between minus 3 and 1. And the question is which one? And the answer is the simplest number. Now, 0 is the simplest number of all. And then you have 1, 2, 3, and also their negatives. And then slightly more complicated than these are 1/2, minus 1/2. Numbers that are 3 1/2 would be actually more complicated than 1/2 because it's bigger. And then is the quarters, and then the eighths, and then the 16ths, et cetera, et cetera. Okay, so we look at the game 1 and 1 3/8 and ask, what's the simplest number that's in between? Well, it turns out there's a number with a fourth, namely 1 1/4, that's in between these two. Even though this involves eighths, we don't have to go to eighths or 16ths to fit something in between. We can actually get something strictly in between that's got a 4 in the denominator. And having a 4 in the denominator is simpler than having an eighth in the denominator. So this is 1 1/4, which is in between 1 and 1 3/8. So when there's a choice of which one to fit in between, it's the simplest one. Now let me actually explain one more thing. Take a look at, say, 1 and 3 7/8. Okay, there's lots of numbers that fit in between here. And the value here, x, that this is equal to a number, x, the value of x here is not the average of these two. It's the simplest thing that fits in between. There's actually a whole number that fits in between, and so it's 2. Okay? You can try one. You can try this at home. Let's try 3/8, 3/4. What's the simplest number that's bigger than 3/8 and less than 3/4? Try it at home. I think you'll find that that number is halfway in between 0 and 1, just to give away the answer. So, and to prove that this number is equal to 1/2, you would have to show this number, this game, minus this game, minus 1/2, is a 0 game. That is a loss for the first player. So there we have it. Games without chance. Let's shuffle the cards and see what I get this morning. This is what I get this morning. That's a really not very good hand, unless you're playing high-low, in which case it's really good. But that's a chance move, and there's no chance moves in this course. The section we're doing now is entitled More Numbers. So, thus far, we have dyadic rationals. But it turns out there's many more numbers. Now, one of the things we've been kind of somewhat ambiguous about in this whole business is how do you feel about games that have infinitely many options? You like them? I do. Mathematicians tend to like games with infinitely many things. Sometimes computer scientists don't because it takes too much space to store infinitely many things. But suppose you had square root of 2. How would you get that as a game? Square root of 2 is not even a rational number, so how can we express it as a dyadic rational? Well, what you do is a trick due to Dedekind, 19th century German mathematician, which is you put all the numbers, on the left you put all the numbers less than square root of 2, and on the right you put all the numbers bigger than square root of 2. So you look at all the dyadic rationals, 1/4. Well, let's see, what is square root of 2? Square root of 2 is 1.4 something, right? So 1 1/4 is less than square root of 2, so 1 1/4 goes over here, in addition to a lot of other numbers. And over here, 1 1/2. 1 1/2 is 1.5, which is bigger than square root of 2. So 1 1/2 goes over here, in addition to a lot of other numbers. So you look at all the dyadic rationals. Every time, square it. If the square of the dyadic rational is less than 2, you put it over here. And if the square of the dyadic rational is bigger than 2, you put it over here. And it turns out this infinite game, because it has infinitely many options over here and infinitely many options over here, is equal to square root of 2. And that way you can get all the irrationals. By the way, you need this actually to get 1/3 also, because 1/3 is not expressible in terms of dyadic rationals. Now, if you're a mathematician, you can have a lot of fun here, because you can do this. Take a look at this game. Take a look at the game whose left options are 0, 1, 2, 3, 4, and keep on going forever, and has no right options at all. Mathematicians actually have a name for this. This is infinity, but in mathematics there's infinitely many infinities. And the infinity that this is called omega. And you can even have more fun. Take a look at the game whose left options are 0 and whose right options are 1/2, 1/4, 1/8, 1/16, etc., etc. Then this is a game that's in between here and here. And so this game is positive. Left always wins, but it's less than any dyadic rational. And so actually this game is called 1 over omega. And so this is infinitesimal, whereas this is infinite. So with games like this, one gets whole bunches of numbers that aren't ordinary real numbers. And in fact, Donald Knuth gave a name to all these numbers that you get, and they're called surreal numbers. Because they contain the real numbers, but all kinds of other weird things. Okay, that's all I have to say about more numbers. Games Without Chance, welcome back. It's kind of wet here today. I hope you're having wonderful weather where you are. No cards today. Oh well. This is the quiz homework. So I'll put up the quiz and then we'll talk about a little bit the directions for how to turn it in and how to grade others' quizzes and all that good stuff is on the course website. So here's a question all about numbers. So in this quiz, there are 5 questions. And the question, the answers are all about what numbers are these games. So the first game is this Hackenbush game that consists of this Hackenbush, and this red one over here. So it's a sum of 3 Hackenbush positions. This is a number. What number is it? 2, 3, and 4 are games that are given in terms of our notation for left options and right options. And game number 5 here is a sum of 2 such things. So for this quiz, I'm expecting for each one of these a number as the answer, and they're usually relatively small numbers with relatively small denominators. I hope you all do well here, and you all come back now, you hear? Good morning. This is Games Without Chance. I'm Tom Morley. Let's look a second. Over here is an ace. Over here is an ace. Over here is an ace. And then we have one more. Okay. So today, this week, we have some modules. And the first one is New Ways of Simplifying Games. So let's look at 2 examples to start with. Here's the first game and the second game. The first game consists of a bunch of numbers for left options or left moves and a bunch of numbers for right options. The second is an up, and if we recall from a while back, or you can look in one of the tabs on the left for all the definitions, up is 0 is the only left option or move, star is the only right option or move, and star is 0, 0. We've previously shown that up is positive, but it's less than any 1 over 2 to the n for any integer n. So let's start with the first one and see how far we get. If you look at this game, left has many options, 3. 3 is many. But the bigger the number is, the better it is for left. So 7 is always better for left than either 1 or 2. So there's no reason the left would ever play 1 or 2, even if this game is in the context of a much larger game and just a small piece. So left, as far as left is concerned, left only will ever play 7. Now on rights, in rights moves, right wants to make numbers games as small as possible. Smaller is better for right, and 8 is less than 10. So right will always choose 8, even if this is a part of a larger context. So these two are never used. This one is never used in best play. So this is the same as 7, 8, and the simplest number in between 7 and 8 is 7.5. So we've simplified game here by using dominated moves. 7 dominates 1 and 2 because it's bigger, and it's a left option or left move. 8 dominates 10 because it's a right option and it's less. So for domination, we want, on the left side, we want bigger, and on the right side, we want smaller. Okay, let's take a look at this game, up and 2. We remember that up is positive and less than 1 over 2 to the n. So since 1 over 2 to the n is less than 2, up is less than 2, all the left options are less than the right options. But I claim this is a number. And it's the simplest number that's in between up and 2, and that's 1. But if you want to prove it directly, all you have to do is show that up 2 minus 1 is 0. And let's see if we can't argue that. If left moves first, left moves to, there are no left moves in minus 1, so left moves to up, and then we have up minus 1, which is negative, so right wins. So left moves first, right wins. If right moves first, right can either move to 2, in which case you have 2 minus 1, which is 1, and left wins, and then you have to check the other cases. But in all cases, if right moves first, right loses. If left moves first, left loses. Therefore, this is 0, and therefore this game is 1. Okay. So here we reduced to a number, even though it wasn't a kind of standard form for numbers. Now, if you go back a long time ago, we looked at NIM way back in the introduction video. We had 3 coins, we had 2 coins, and we had 1 coin. And the rules of NIM are each player in turn can remove must remove 1 or more coins from one of these piles. Now this is an example of what's called an impartial game, which means that the rules are the same for both players. The negative of this game is the same as this game. And one of the things I asked you to think about in terms of this game in the introduction video was who wins this game, and in terms of what we do now, who wins this game is the second player. Whoever moves first loses. Okay. So let's ask if extra coins help here. So I have this NIM game with these 3 NIM piles. Let's see, I have them in, that's a pile of 1, that's a pile of 2, and this is a pile of 3 over here. I'll put them under their numbers. Star integer is just a notation for a NIM heap of that size. NIM heap of size 1, size 2, and size 3. Now, if someone gives you some extra quarters, does this help you in any way? So we already know that if you remove any of these, then the player whose next move it is has a winning move. So the only possible winning move is perhaps to put more coins on here. So I've put a bunch more coins on there, and it's a lot. You can count them if you want. Now, what is the response to this? The response to this is the other player just removes the coins that you just put on and puts $1 25 in his pocket. Now you're left back where you started. It's still your move, and now you lose again. So if it's your move, and instead of removing a coin from here, you put on extra coins, then the other player just removes them, and you still lose. So the extra coins don't do you any good. Now, in terms of our vocabulary for talking about games, this is called a reversible move, because once you make this move, the other player just reverses it, and we're left back where we started. Okay, this is the end of Module 1. Thank you. Welcome back. Tom Morley, Games Without Chance. Actually, that's not so bad. There's some game you play with these, I think. It has chance in it, so we won't use it. We're looking now at examples from NIM. And let's look at it. Now, NIM is an example of an impartial game. So what we're going to do is abbreviate impartial games like this. So what this means is the left player has the option of moving to a NIM heap of size 0, 1, 3, or 7. And the right player has exactly the same options. The right player can move to a NIM heap of size 0, size 1, size 3, or size 7. Now, my claim is, so we can either leave 0 on the table, leave 1 on the table, leave 3 on the table, or leave, let's see, how many more do we need? Leave 7 on the table. And then the other player can do so. Why is the, okay, ooh, oh, that's kind of proof-like there in the camera. So that's the game. Now, this is not, by itself, not an interesting game, but it can be part of a larger NIM game with other stacks of coins on the table. Now, let's analyze this. In terms of analyzing this, my claim is this is a disguised version of a NIM heap of size 2. Why? Let's take a look at what you can do with a NIM heap of size 2. With a NIM heap of size 2, you can leave no coins on the table, that's star 0, or you can remove 1 coin and leave 1 coin on the table, and that's star 1. So that's star 2. Now, this up here, these 2 moves don't do you any good because they reverse. If you put down 3 coins, the other player removes 1 and we're left back with star 2. If you put down 7 coins instead, 1, 2, 3, 4, 5, 6, 7, then the other player removes 5. Is that right? Is that how you do arithmetic? Check it with your calculators. Okay, and then you're left with 2. So these 2 moves are reversible. If you ever make those 2 moves, the other player can reverse straight back to star 2. So this impartial game is actually star 2. It's actually the same as a NIM heap of size 2. Try one for yourself. What about this one? Star 1, star 0, star 2, star 101. Try that. See what you can get. You should conclude that this is the same as a NIM heap of size 3. Short module this time. Y'all come back now, you hear. Hey, welcome back. Good to see you. Although I can't really see you, but I'm looking that way, and it looks like I can see you. Okay. What are we doing now? Examples from up, down, and star. Now, and the general reversible move. This is probably one of the most subtle things we've done in the whole course. And it's not something that's easily converted into hand computations and examples. So if this seems like you have to go back and look at it over and over again, that's okay. It's something that's a little bit more complicated than some of the other stuff we've done. What I want to do is look at the general reversible moves and then do an example. And the example is very, very small. So what's really going on in talking about reversible moves is this is what's part of the general engine inside computer programs that analyze these things. And although we can compute small examples by hand, you can't really do much bigger examples by hand. So bear with me. So here's a whole lot of text, and the definition of reversible moves in games without chance. So we start off with a game which has certain left options or moves and certain right options and moves. And then we say this game reverses through one of the left options or left moves. If there's a right move of this left option, call that AR, with AR better for right than G is. So remember, if a game is less, it's better for right. So this means AR is better for right than G was to begin with. So think about it this way. Left moves to A, then right immediately moves to one of the options inside A, namely AR, and right now is better off than when right started. So right may as well do that. Left moves to A, right immediately is better off by moving to AR, is better off than he or she was when the game started. In that case, right may as well do this all the time whenever left moves to A, and therefore left might as well move directly to the left options of AR rather than to A itself. Now that's a little bit complicated. We'll look at an example, so don't panic yet. All right. I read some book that had this in it, right? I've forgotten what the book was. Don't panic. Okay, it was a book of advice. And whatever you ask it, it said, don't panic. All right, so don't panic. Now, in games, we always have to look at things from the point of view of left and the point of view of right. So here's the analog for reversing through a right move. Now, so here's an example, and feel free to go back and look at these definitions again, ask questions about them in the forum, and to relook at this example. So here's the example. The example is up plus star. Now up is left move, only left move is to 0, the only right move is to star. Star is the only left move is to 0, the only right move is to 0. So up plus star is the same as this plus this. So we have two games. We play them, their sum by playing in one game or the other. So let's look and see what happens. Left can move to this 0, make that move, in which case what's left is 0 plus star, so that's star. Or left can move over here to this 0, in which case what's left is 0 over here and up over here. So the two possible left moves leave star and up. And now let's look at the right move. The right can move to star, in which case you have star plus star. You can check it out, star plus star is 0. Or right can move to this 0 over here, then you have 0 plus up, and that's therefore the other right option. Now, let's look at this. So the first thing we want to notice is the following. I'm going to recopy some of this. So up plus star is, by our computation, star, up, 0, up. Now, we know that 0 is less than up from a few slides ago. Remember, 0 is less than up, is less than 1 over 2 to the n for any n. If you look back, this was actually done in one of the earlier weeks, although maybe we didn't actually write it that way. So that says this up is always worse for right than this 0. 0 is always better for right than up, so this move is dominated, so we can delete it. Okay, that's the easy part, or the easier part. All right. So now let's look at this up. Up, that up is 0 star, and so it has a right option of star, right move of star. Now, star is less than up plus star because just subtract star, just add star to both sides. Star plus star is 0, and over here we'll have up plus star, which will be up. So since 0 is less than up, we have this, which says that there's a right option of up, this up here, that's better for right than the original game. So right will move there automatically once left moves to star, and then left is left with the if left moves to up, right moves to star, and then since star is 0, 0, the only left option from there is to move to 0. Go back. Rewind the video, look at the definitions. That says this reverses to 0. 0 is the left options of the right option of up, provided, which is better for right than the original game. I think I said that right. So that says up plus star is actually 0 star 0. Now, where have we seen that before? Take a look at this position here, Hackenbush. Green edge down here, blue edge up here. Blue can cut the blue edge, left can cut the blue edge, in which case what's left is star, or left can cut the green edge, in which case what's left is 0. Right can only cut the green edge, in which case what is left is 0. So these are equal games, and they're both equal to up plus star, which is sometimes abbreviated in literature as up star. So it turns out that we've seen this game before, and now viewing this game as up plus star, we, for instance, know what happens when we add it to itself. So up star plus up star is up plus star plus star. But star plus star is 0, so that's up plus up, which is sometimes written in the literature double up. So double up to be sure, and we'll see you next module. Welcome back. We have, what do we have? We have a straight flush, small values, but nonetheless a straight flush. Not quite in order, but you can check it. We're doing toads and frogs now. You can do this at home with people, and it's fun to play with people. But you can also do it with with coins, here's toads and frogs. Let's use nickels over here. And Jefferson nickels, let's use Lincoln pennies over here. Here's toads and frogs. The toads in this case are the nickels. They move right and are controlled by left. The frogs are the Lincoln cents. They move left and are controlled by right. The toads can move one space to the right if it's empty. The frogs can move one space to the left if it's empty, but they also can jump over each other. A toad can jump over a frog like this. Note that the coin when you jump over isn't removed. Okay. But you can jump over, and then they then say the Lincoln cent can move over here, the nickel can do here, the Lincoln cent can move over here, Lincoln cent is the frog, and we see at this point that neither the toads nor the frogs have moved, so this Lincoln cent, which was a frog, was right. Right made the last move. It's now left's turn. Left doesn't have any moves. Left loses. Okay? That's toads and frogs. And there's lots of examples involving up, down, and integers and all that good stuff involving small versions of toads and frogs. So you can try this at home. You can either do this with coins on a piece of paper, or get your friends, and that way you can jump over one another, and you draw these on the floor. Okay, all right. So, but be careful and don't hurt yourself, and don't try that at home. Probably do it with coins. All right. So let's look at a toads and frogs position. Now, here we have toad, toad. They move right. They're controlled by left. Blank means an empty space. Frog, frog. Frogs are controlled by right. They move left. The only possible opening move for left is to move this toad one to the right, and that leaves toad, blank, toad, frog, frog. And the only possible opening move for right is to move this frog one left, and that's leaves the position toad, toad, frog, blank, frog. Now let's go over here and look at this position. If left moves in this position, then this toad moves to the right, and we're left with toad, toad, frog, frog. That's a 0 position, okay? If right moves, then right can jump over, take this frog. The only possible case is for right to move this frog, jump over the toad, and left with toad, frog, toad, blank, frog. Now, let me remind you that when we're analyzing games, we have to consider like 2 left moves in a row and 2 right moves in a row, because we want to analyze this game in the context of a much larger game. So we might have this toads and frogs over here. We might have a NIM game someplace else, cut cake someplace else, a game of chess going on, and a game of Go going on, and then each player in turn chooses one of these games and makes a move in it. This is how we add games. So, and in doing so, in adding this game to others, left might make two moves in a row in this. Okay, so I'm going to leave out some pretty long, I think, computation, but this game down here, toad, frog, toad, blank, frog, is actually equal to star. So we have this game up here, toad, blank, toad, frog, frog. Its only left option is to move to 0. Only left move is to move to 0. The only right move is to move to star. Therefore, this game, toad, blank, toad, frog, frog, is up. Up, we remember, was left 0, right star. Now, if you look at this game over here, it's the same as the game over here with toads and frogs interchanged and left and right interchanged. Just take the mirror image and change all the toads to frogs and all the frogs to toads. Therefore, this game on the right is the negative of the game over here. So this game on the right is minus up, which is sometimes written down. So this whole game is equal to up, down. And that's what I want to look at in this module. Okay. So, there are no dominated moves because there's only one move possible for each player. But down here, if up is 0 star, then down is its negative, which is star 0. Remember that the negative of star is star, and the negative of 0 is 0. And so if right moves to down, left can move to star. And my claim is star is better for left than the original game. That is to say, G is less than or equal to star, which is the same thing as adding star to both sides. G plus star is less than or equal to 0, which says that right wins this game going second. Okay, there's a little bit to show there. So, but what this means is that if right moves to down, left moves immediately to up, right moves to down, left moves immediately to star, and now since star is 0, 0, the right possibilities for to move from star are only 0, so this reverses all the way down to just 0. Which means that if right plays down, left immediately plays star, and then right's only option is down. So this says that G is actually equal to up 0. And this game simplifies a little bit, but that's part of the exercises, homework, quiz, whatever you want to call it for this week. All right. Now, let me make some general comments about this. Simplifying games. We came up with 2 ways of simplifying games. Dominated moves. We can delete dominated moves. If a move is better for left than another move, then you never have to do the poor move. If a move is better for right, you never have to use the move that is better than. And reversible moves. And that's a little complicated, but we have some examples. And that's probably technically the most complicated thing in the whole course. Now the question is this enough? That is, are there other possible ways of simplifying games? Of course there are. But what one can show is that this is enough in the sense that if you keep doing dominated moves and reversible moves and keep doing them over and over again, you'll reach a point where no moves are dominated, no moves are reversible, and what's left is called the canonical form, and that's unique. And there's and that's in some sense, some technical sense, in fact, that one can make very precise, the simplest possible version of that game. So all that you really need is this. Now, in terms, and that's how some computer programs, and you can look up which ones are available, open source on the web, actually simplify games. And they keep doing dominated moves and reversible moves over and over again until there aren't any. And then when it's left, they say this is as simple as possible. And that's what it is. Okay, let me just leave you with this, which will be posted in the assignments, etc. And the directions this week are simplify. So write down the simplest form of each of these games. Number 1 is numbers over here, numbers over here. 2 and 3 are turn out to be numbers, I think, but you try it yourself. Number 4 was what we ended up with in the exact last answer. We took up, down, and simplified to this, and now we want to simplify this further. The last one is the toads and frogs position. Remember, frogs move right, toads move left. Take this and see if you can come up with the simplest possible description of that. And we'll see y'all in a week or two. Take care. Next week, I think, is NIM. We finally will analyze NIM in general and answer the question, with an arbitrary NIM game, how do you play it and win? So we'll see y'all next time. Take care. Oh, hi. Good to see you back. Give me a second. I'll be right with you. Hey, so here we are. Let's cut the deck a few times, see what we have. Maybe once more. Okay, here's your card, my card, your card, my card, your card. Ooh, what's that? Ooh, another king. You did good. My card, your card, and my card. Ooh, I got an ace. What else did I get? I got all aces. No chance. Okay, here we are in week 6. Well, so what was the chance of that? As advertised, week 6 is all about NIM, how to win it. All about impartial games, reversible moves. Examples, minimal excluded function, and the big theorem due to Grundy that all impartial games are equivalent to NIM. So let's start off with NIM and how to win. Okay, star n is our game. It's an NIM heap of size n. If you go back and look at the introduction video, you know, that's like a year or 2 ago, we looked at the NIM heap of size 1, 2, and 3 played together. That's star 1 plus star 2 plus star 3. First player loses, so that's 0. And we say that in terms of game theory, star 1 plus star 2 plus star 3 is 0. Okay, let's look at one NIM heap all by itself. This is not very interesting. So here I have a NIM heap of 4 dice. Now, whoever comes along just picks them up, and they're all gone. So a NIM heap all by itself is a loss if there's, to the first player, if there's nothing there. And it's a win to the first player if there's something there. Okay? So that takes care of one NIM heap all by itself. So it turns out that the sum of a bunch of NIM heaps is equivalent to another NIM heap. And D, the size of the NIM heap that's computable, which is called the NIM sum of A, B, C, D, that's A, B, and C, etc., is computable from that, and it's called the NIM sum. And what we just proved, or in the introduction video, we kind of used the fact that star 1 plus star 2 plus star 3 is 0. Star 0 is the same as 0. And so what this says in terms of NIM sums is the NIM sum of 1, 2, and 3 is 0. Another example, which you can work out after we say how to compute NIM sums, is that star 2 plus star 3 plus star 7 is star 6. I hope that's right, but I'm not very good at arithmetic. There are 3 kinds of mathematicians in the world, those that can count and those that can't. All right, so let's compute this. So here's how to compute. Let's look at an example. I want to compute the nim sum of 14, 11, and 2. So how many kinds of mathematicians are there in the world? There are this many, and that's 2 because this is binary. Binary is just like base 10, except instead of 10 fingers, you have just 2 fingers. 1, 2, 3, 4. I can't do that. 1, 2, 3, 4, et cetera, et cetera. So 1, 2, 3, 4, 5, et cetera, et cetera. So we can count like that. That's binary. You all can look it up. It's not something new. It's been around for a while. And ultimately inside computers is binary. So computer scientists know all about that. There are 10 kinds of computer scientists, and this actually means there are just 2. All right, so 14 is 1110 in binary, because 8 plus 4 plus 2, 8 plus 4, yeah, it's 14. I did that right. 11 is 8 plus 2 plus 1, and 2 is just 2 all by itself. And here's how you compute the nim sum. You add these up column-wise, but just mod 2. So 0 plus 1 plus 0 is 1. 1 plus 1 plus 1 is 1 mod 2. 1 plus 0 is 1 mod 2. And 1 plus 0 is 0 mod 2. So the nim sum of 14, 11, and 2 is 0, 1, 1, 1, which is 4, plus 2, plus 1, which is 7. Okay, here's how to win the nim game. If you have a heap of size 14, a heap of size 11, a heap of size 2, their nim sum is not 0, so therefore there's a winning move if you start. And let me show you how to do the winning move. You take the answer here, go and find the rightmost, ooh, that's not rightmost, that's leftmost. Find the leftmost one, go up here and find one of the numbers that has the 1 there and circle it. Okay? Now take what's to the right of that, 0, 1, put it over here. Take this down here, 1, 1, and now do the same thing to here. 1 plus 0 is 1, and 1 plus 1 is 0, again mod 2. So we take 1, because that's already there. Take this 1, make it a 0. Make this a 0 and make this a 1. So that comes from the 0, 1 over here. So that's 1, 0, 0, 1, which is what? That seems to me that's 8 plus 1, that's 9. So take the 14 heap and remove, how many? 5 coins, so it's now 9 heap, and that's your winning move. Okay? Here's something for you to try. Start with a nim heap of size 11, a nim heap of size 13, a nim heap of size 10. If this is a win for the first player, find the winning move. If it's a loss for the first player, then give up. Or at least offer the other player, say, why don't you go first? That's the end of the first module. Okay, welcome back. It's still week 6. Wow, one more week to go. So here we're in partial games, reversible moves, and we'll have a few examples and mechs, but I think that it's going to be 2 pieces. So let's take a look at this. So let's talk about impartial games. An impartial game is where, like nim, both left and right have the same possible moves. Not like 5, which gives 5 moves to left and no moves to right, or -5, which gives 5 moves to right but none to left. 5 and -5 are partisan games. They're games where it depends on whether you're left or right, whereas nim is impartial. In general, a game is called impartial
if every left move is also a right move and every right move is a left move, and every move in every position is also an impartial game. So let's look at an example. Okay, now when we write down the impartial games, we don't have to say what the left moves are and what the right moves are. All we have to do is say what the moves are. This is because every left move is a right move and every right move is a left move. So let's look at the game where the moves are to a nim heap of size 0, size 1, size 2, size 5, or size 7. Okay, so my claim is it's the same as this. So think of this as a nim heap of size 3 that you can add 2 coins to, or you can add, let's see, 4 coins to. So start with a nim heap of size 3, and either you remove 1 or more coins, or you add 2 coins, or you add 4 coins. That's this game G. Now, if you add 2 coins, I'll just take them away and put them in my pocket. And if you add 4 coins, I'll just take the 4 coins and put them in my pocket. So the move to star 5, to 5 coins, which you get by adding 2 coins, and the move to star 7, which you get by adding 4 coins, is irreversible. The other player just takes them away and pockets them. And if they're like something really exotic, like a rare year of the Morgan dollars or something, it might be worth something in say, grade 65 or so. That would be worth a lot of money. So if you add coins, the other player can just take them away and you're back to where you started. What this says is this game here is the same as this game here, but this game here is the same as just a nim heap of size 3, which you can, and the moves from a nim heap of size 3 are to a nim heap of size 2, 1, or 0. And we note here that 3 is what's called the minimal excluded number out of 1, 2, and 3. That is, you look at 1, 2, and 3 and look at the first natural number that's missing. And in general, what happens, so let's take a look at some examples of mechs, and we'll leave that for you to compute for next time, and then we'll have go back to examples of games. So the minimal excluded of 1, 3, 2, 1, 17, let's see, 1 is there, 2 is there, I'm sorry, 0 is there, 1 is there, 2 is there, 3 is there, 4 isn't, so it's 4. The minimal excluded of this is, well, 0 is not there, so it's 0. And the minimal excluded of this is 5, if I did this correctly. And so here's the minimal excluded for you to get. Now, it occurs to me that I didn't do the problem from last time. And so let me just leave up some numbers here. If we take a nim heap of size 11, 3, and 10, 11, 13, and 10, write them out in binary. There's a 1 here, go up to the 1 here, circle that. 101, take 101, nim sum 1, 0, 0. We get, what do we get? We get 0, 0, 1. So the winning move is here is keep the 11 the same, take the 13, and change it to a 1 and take the 10, and it's the same. So that's the solution, I believe, to the problem at the end of the last module. And there we have it, end of another module. Okay, welcome back. Still week 6. And we're doing some more examples and talking a little bit about minimal excluded. Okay, so let's take a look at this quickly. We have some examples of minimal excluded, and excuse me while I look around the camera. Okay, so let's see, 0 is here, 1 is here, 2 is here, 3 is here, 4 is here, 5 is here, 6 is here, 7 is here, 8 isn't. So the minimal excluded of this is 8. And so that's the solution from last time. All right, here's the general result. If we have an impartial game, all of whose moves are to nim heaps,
then this game is equivalent to a nim heap of size D, where D is the minimal excluded natural number in the set consisting of these A, B, C, A, B, dot, 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 up to C. So the example from last time fits this context. Here we have this. Here's a game. All of the options are nim heaps, and 3 is the first missing number, and so this game is equivalent to nim heap of size 3. Okay. Let's take a look at, and any of these things we can think of as nim heaps, where we can add more coins, but you can always reverse those moves by putting the coins in your pocket. All right. Let's take a look at a case, another kind of case, another kind of game. It's called a subtraction game. So we start with a heap of size n may be 1, 2, 3, or 17, or 40 billion. A move for either player is to remove 1, 2, or 5 coins, or beans, or dice, whatever they are. Or bicycles. We could have a heap of bicycles. That would be fun to play. Okay. So let's take a look at that. If we start off with a heap of size 0, then there's no moves, and so that's equivalent to a nim heap of size 0. If we start off with a nim heap of size 1, we start off with a heap of size 1 and play the subtraction game, 1, 2, or 5, then our only move is to a heap of size 0. That's 0, and then mex of 0 all by itself is 1, so that's a 1. Now, with a heap of size 2, we can remove 1 coin, giving us a heap of size 1, equivalent to a nim heap of size 1, or it can remove 0 coins, giving us equivalent to a nim heap of size 0. The mex of 0 and 1 is 2. For 3 coins, we can remove 1 or 2, so we can replace this by a heap of size 1 or 2, which is equivalent to a nim heap of size 1 or 2, and the mex of 1 and 2 is 0. For a heap of size 4, we can remove 1, giving an equivalent to a nim heap of size 0, or 2, giving an equivalent of a nim heap of size 2. The mex of 0 and 2 is 1. For 5, we can remove 0, 1, or 5. Ooh, there we go. All right, I feel like I'm playing the piano or something. All right, and so the mex of 0, 0, and 1 is 2. For 6 here, this is for you to figure out, and we'll start next time with the next module with this. So I can, it goes back to removing 1, removing 2, or removing 3. So what do you think that should be? Okay, not too hard. So what we can do is say the following in general. We can have subtraction game where we remove A, B, dot, 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 or C coins. The first player with no move loses. And G of n is D, and this it's the size of the nim heap equivalent to this game. And this can be computed in exactly this way. And I think we're done. Beep. It only works if you make a noise. Take care. Okay, welcome back, week 6. I just rolled the dice. They all came up that way. You believe that? It's pretty dark in here. I wish they'd turn up the lights or something. I don't know what's wrong in the studio here. Let's see. Oh, it's not so bad. Okay, so this week is a big, big theorem due to Grundy, I believe in the early 20th century, 1930, late 30s is my guess. Y'all can look it up on the interwebs or whatever it's called. And here's the theorem. Okay. But let's first go back and answer the question from last week. Okay, so we're at 6. We can subtract 1, 2, or 5. That's my subtraction game. 1, 2, or 5. So 1, 2, there it goes. So that's the mex of 1,
1 and 2 is 0, so it's 0 here. And I bet you the next one's a 1, and I bet you it goes 0, 1, 2, 0, 1, 2, 0, 1, 2, 0, 1, 2, forever. It's periodic. A lot of these impartial games are, if not periodic, at least ultimately periodic. After a while, they're periodic. And what this means is something very important in terms of computational complexity. It says we can solve all of the games in a finite amount of time. They all reduce to a NIM heap of size 0, 1, or 2, regardless of how big they are. And we can tell which one it is simply by calculating mod 3. It's important. A theorem like that for the game Chomp won one student once $100,000 in a science fair. You can look it up. All right. Theorem de Grundy. If G is impartial, then G is star n for some integer n. So every impartial game is equivalent to a NIM heap. And an example is our same example as before. There we go. You look at the minimal excluded. So here's the proof. And so don't panic. It's a proof. You know, mathematicians do these kinds of things. And it's induction. And the proof is so short. Ooh, they sit here and make noises. Okay. The proof is so short that you kind of wonder afterwards, did I really do anything? The answer is yes, you did. You proved a theorem. That's a big deal. All right, so I will do induction. If G is 0 game, then G is already equivalent to NIM heap of size 0. Piece of cake. All right, so suppose G is impartial, then by induction, the options of G, the moves of G, are themselves equivalent to NIM heaps. This is by induction. These are simpler games than G, so assuming that the theorem is true for all simpler games, all of these are equivalent to NIM heaps. And now we're basically back to this same old example. Where is it? Well, basically, the same example. If you have something like this, this is a NIM heap with possible adding coins, but adding coins doesn't do you any good because the other player can just take them away. Okay. Let me do an example here which relates back to what we started with this week, and that's NIM sums. Okay, NIM sums. So let's take a look at star 2 plus star 3. This theorem ought to tell us about how we compute this. So suppose we don't know about NIM sums, and we just want to compute them. So star 2 is this game here, and star 3 is this game. And so if you add them together, what do you get? You take one of these plus this, that's 0 plus 3, or this plus this, that's 1 plus 3, or you take the whole thing here plus 0, that's star 2 plus 0, or you take star 1 plus star 2, that's this option plus the whole game over here, or you take star 2 plus this whole game, which is star 2. So just by the definition of addition, star 2 plus star 3, which is this plus this, is this. Now, 0 plus anything is anything, so that's a star 3. Star 1 plus star 3, well, that's a simpler game, and we suppose we've already computed that. We actually know how to do that. That's 0, 1 plus 1, 1 in NIM sum in binary, which is 2. 0 plus 2 is 2, because 0 plus anything is 0. 1 plus 2 is 3, both in ordinary arithmetic and NIM sums. And 2 plus 2 in NIM sums is 0. So star 2 plus star 3 is this. And if you look, 0 is here, but 1 isn't, so the minimal excluded is 1. So the whole thing is equivalent to a NIM heap size 1. And we knew this already. If you take a NIM heap of size 2 plus a NIM heap of size 3 is equivalent to a NIM heap of size 1 because the NIM sum of 2 and 3 is 1. Okay. Let me give you another game, slightly more complicated. that y'all can talk about in the forums. We're not going to solve it explicitly here, although I may comment in the forums. And it's star 0.4. And we have a stack of coins. Remove one coin and split into two non-empty piles. So if you start off with 0 coins, then there's no moves. And if you start off with 1 coin, there's no moves. And if you start off with 2 coins, there's no way to remove 2 coins and split it into 2 pieces. There's no way to take 2 coins, remove one of them, and take the remaining 1 coin and split it into 2 non-empty piles. So that's 0, 2. 3 is the first non-trivial case, and you can work it out and work out some higher ones. This is an interesting game called 0.4. And if you want to look this up in the internet or someplace else, it's called TheGame. All right. Let's look at the quiz for this week. It's find the nim sum of 1, 5, and 11. Find the mix of that set. For the subtraction game 1, 2, 5, find this G of 7, and find G of 4 for the subtraction game 1, 2, 3. Okay, so and this will show up actually on the quiz, and you'll have a little bit of time to do it. I think they're straightforward. If they're not, let me know. And that's week 6. Y'all come back now, you hear? Cut! Wrong class. This is Game for That Chance. Tom Morley. And this is week 7. Where do we go from here? Our first little piece is on infinite and loopy games. Now, we previously looked at Hackenbush games, and if they were red-blue, they were mostly numbers, and if they had green stalks in them, they were these weird nim things, and they could add them and all kinds of good stuff. Now, you can actually do infinite numbers in this same way. Take a Hackenbush, all blue, all the way up, and keep on going forever, and that's the number which mathematicians call omega. Now, that's infinity, but there's one larger than that. Namely, take an infinite stalk that goes up like this. The stalks are getting shorter and shorter, but there's still infinitely many of them, and they keep going along like that, and then put another blue stalk on top of them. And that's omega plus 1. And you can take infinite stalk, getting smaller and smaller and smaller, but still infinite, keep on going forever, and put another infinite stalk on top of it, keep on going forever, and another infinite stalk, keep on going forever, and that's 3 omega. And you can look at omega, omega, and omega, 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 and you can get larger and larger and larger. All of these are what mathematicians call ordinal numbers, but these, together with real numbers, sit inside a number system called the surreal numbers, which includes the numbers that we talked about in games, the infinite numbers. And if you want to know more about this, there's a famous book by Donald Knuth called Surreal Numbers. And that's what I want to say about infinite games and loopy games. Take care. Okay, Games Without Chance, a little short one on 1B, loopy games. Now, there's a famous comedy skit about argument, and these two people sit down and they have an argument. And one person says, look, argument is not just about contradicting one another. And the other person says, yes, it is. No, it isn't. Yes, it is. No, it isn't. Yes, it is. This is an example of a famous loopy game that children like to play.
although I wouldn't encourage them all that much. And it's called Tisn't. Now in this game, in loopy games, we represent where we are by nodes, and the two nodes are called Tis and Tisn't. And the blue player can move from Tisn't to Tis, and the red player can move from Tis to Tisn't. And yes it is, no it isn't, yes it is, no it isn't, yes it is, no it isn't, yes it, and this goes on for, as long as they want to play. It's kind of fun. Here's a more adult game you can play that's loopy, or possibly loopy. It's called Fair Shares and Varied Pairs. So what we have is a bunch of beans or counters, I'm using quarters in this case, on the table in various heaps. Now what can happen is there are two kinds of moves. You can take a heap of quarters and divide it into, say, 2 heaps of equal size, or maybe 4 heaps of equal size. But in any case, you can take any heap of quarters and divide it up into any number of heaps as long as they're the same size. That's called the fair shares part. The varied pairs part is you can take 2 heaps as long as they have a different number and combine them into a single heap. Now, because we can combine heaps and separate heaps out, there's a real possibility the game loops on forever. However, this is a really fun game to play at parties. Try it with almonds or walnuts, or if you're in the South, try it with pecans or pecans. I never knew which way to say it. In any case, and then, of course, the first player who can't move loses, and the losing position is all heaps of 1. There, you can't separate them all out, and you can't combine them because they're all equal. And so this is the losing position. Whoever's presented with this position here loses because there's no possible moves. So here's a little bit about loopy moves, and we'll be back in a few minutes with a little bit about Sente Gote. Morning, afternoon, evening. Games without chance, and week 7, and we want to talk about mean values, hot, cold, Sente Gote. So, and if you have a Japanese dictionary, you can look up the last 2 terms. All right, mean values. One of the things we looked at a little while ago, at least in some of the extra problems, were these games, for instance, like these. And these are games called check games, cashing checks. And in these games, people really want to play them. But when you played sums of these games, people grabbed the games. If this is the game G and you played G plus G plus G, if you played sums of these, they behave just like numbers, or very much like numbers, or close to numbers. This can be generalized, and there's actually a theorem behind all of this, which is called the mean value theorem, although not the same one as in calculus. And it says, given any game, there's a number m of g called the mean value of g, such that and a number k, independent of n, such that when you add up gn times, that this minus n times the mean value, that this is within a bound which doesn't depend on n of a multiple of the mean value. So large number of copies of G played together behave approximately like a number. And as n gets large, k doesn't depend on n, so k is small relative to n. So as n gets large, this approximation gets better and better, at least relatively. This is called the mean value theorem, and analysis of this, together with the actual construction of the calculation of the mean value, called the thermograph, allows us to have a number of strategies that are not optimum, but are actually computable, and in some sense within a bound of being optimum. That is, they're not necessarily the optimum strategy, but they're guaranteed to be not too bad. And these are often based on, you have a sum of a large number of games, and then the real question in terms of playing a game decently is which one to play in. So you have a sum of all these games. Do we play G2 first, or GN, or G1, or whatever? And if our opponent plays in G2, should we respond in G2 or go to a different game? And so this is our Japanese terms, sente gote. Sente means, to have sente means that you play a move and you force your opponent, you have the initiative. The opponent has to respond to your move. Gote is the opposite, where you play and your opponent can play in some other game. So in sente, you play, for instance, in G2, your opponent is asked to respond there immediately. And in gote, maybe you play in G2, he says, no problem, I'll play in G5 over here. So there's a whole class of strategies and approximate strategies and interesting constructions having to do with the mean value and various ways of finding it, which give rise to approximate strategies for playing games, and an analysis of whether you have sente or gote. Okay, next time. Hello again. Games Without Chance, Tom Morley. Let's look at atomic weights. Now, let's look at one of our favorite games, a NIM heap of size 1. Not terribly exciting. No one's really, oh, let's go play a NIM heap of size 1. Nobody's really that excited about it. But this is a new symbol. That's an integral sign, but this is the way the sign that's used in the theory, and it has nothing really to do with integrals. This is the heating of star by 3. So instead of 0, you say 0 plus 3 over here. Instead of 0 over here, you say 0 minus 3. And this is a heated game. And this is a hot game because left wants to play this because then left gets 3 points, or 3. And right wants to play this because then right gets 3 points, or minus 3 to left. So this is a hot game. So we started off with a really kind of boring game and created a hot game. Good. Now, a result that Simon Norton is that any game is actually a number plus a sum of heated versions of infinitesimals. Okay, infinitesimal would be a game that's less than 1 over 2 to the n for every n, and greater than minus 1 over 2 to the n for any n. So you can't know anything, you can't know all about games unless you know all about infinitesimals. And infinitesimals can be really complicated. So here's one way of analyzing at least a very large class of infinitesimals. A game is called all small if whenever left has a move, so does right, and whenever right has a move, so does left. And this is true for both the game itself at any position possible in play. So for instance, the game 0, this is the game 1, I believe. This left has a move, but right doesn't have a move, so this is not all small. So and all smalls are you can prove are infinitesimal. Now here's the result. And this is computable. And this is probably actually the most complicated or most intricate or long proof in Winning Ways Volume 1. If G is all small, then there is a game capital G, computable from G in various ways, and they go through the ways it's computable, such that capital G times up, so this is a multiple of up, we have to eventually say what that means, So that g minus this multiple of up is pretty close to 0. It's caught between up plus star plus an unspecified nim heap, and greater than or equal to down plus star plus an unspecified nim heap. And from this, this is another approximation result, that an all small game is very nearly, subject to this error, a multiple of up. And this can be used to analyze the play of all small games. But enough of this theory. Let's look again at divided fair shares and varied pairs. If you remember, what we have for fair shares and varied pairs is that you can, it's here somewhere, you can take a coin, take a stack of coins and divide it into any number of equal stacks, or you can take two stacks that are not equal and combine them. So this is a fun party game. Let's start with a stack of 3 over here, a stack of 3 over here, a stack of 2, and a stack of 2. And let me remind you, you can take any stack, divide it into any number of equal stacks. You can take any 2 unequal stacks and combine them. So here we have a stack of 3, a stack of 3, a stack of 2, a stack of 2. 10 coins in total. Go ahead. It's your first move.